All right. Then continue with where we were last time. So he was going to finish talking about PID controllers. All right. We talked about pole placement. And we talked about talking about PID, and then we're going to talk about linear quadratic regulators next week. So we just find book and the chapter that we're talking about and just proceed. All right. So finding chapter 9. Okay. So if you recall, let's share this. All right. So last time, we're on chapter 10. Last time we were talking about PID controllers, and so let me just recap quickly what we were saying. Can just find the spot. Okay. All right. So this was where we were last week, and so we said when we had a first order controller, we had to determine the log, where we didn't have to determine what this was the system gain. The K was the system gain, and the T was the time constant. And we had said that you could find the equation. I'm sorry, never do any work on it, what I said I was going to do last week. But said that the point of if you have an experimental plot, the point where the gradient is the steepest is the point at which we would find the tangent to the curve, and then that tangent we are going to use, find the equation of that line, the tangent at the point where the steepest curve. So this is the point of steepest slope. And then where it cuts the axis and where it crosses the line for the gain, that distance there would be our time constant. But we had said that you could work out the time constant by finding 63% of the final value. That's T, would be 63% of the final value. And the lag time, if you had a proper graph, then the graph would look like that. And your lag time would be the time between when the curve starts to rise to your zero axis. Right? So your time t equals 0. So your lag time would be given by that. So you would find 63% on here for, so that would be your t. 63% would be your lag time. You don't need k, but k is the final value that we'll go to. Right? This is a special, this graph that is drawn here is a special case in that it starts at t equals 0. The graphs don't usually start at t equals 0. Where there's a delay, there's a noticeable delay, and then you can use that to read off your lag time if you are conducting an experiment. The other thing that I need to point out is that you apply a step input. Right? So you apply a step input. So its step input will be 1 volt, 1 amp, whatever 1 of whatever the thing is, that is the step input that you would apply. All right. And you want to get these values, the time constant and the lag time. Okay, so if the graph doesn't start at 0, then you can easily read off the lag time and the time constant from the graph. All right. So that was what the discussion was about last week. We had said that you could pick your controller, you pick a PID if the system is prone to noise, whatever the form that noise is. This is systems that have slow response time. This is just for slow response time and not prone to noise. Means that there are no big, if you don't expect to see a graph like that. You don't expect to see nice spikes. So like the kiln at Jamarco and Alcan and those places, the temperature rises pretty slowly, and you don't expect any big jumps in the temperature at any point. So therefore, you use a PI controller for that. The PID controller is when you have a system that is prone to this kind of nice spikes. And the proportional controller can be used for anything, but you would normally put it with a PI or PID controller. There's also a PD controller, but for our discussion on for our discussion, all that would be is that I would be equal to 0 if 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 required. But you don't normally see it when we're talking about this method of tuning that we have. All right. So that was basically what we said last week. But what about this week now? So this week we want to talk about what the textbook has as the second method. And the second method is for second order and higher systems. So what we're going to talk about today, suppose, let me rephrase that. This is for systems with a second order type of response. So what we were discussing last week is systems with a first order type of response. So just to remind you, the second order type of response that we're talking about is one that does that. First order type of response is one that does that. So the second order response is one that behaves in that way. So the method that we're going to talk about now is for second order types of responses. All right, so we're just going to write it down out of all of this. Now, if, let me make the right down there and come back to this. Mhm. All right, so let me just try to summarize what is in the that. So there are some things that we need to find out. So one is apply. So this is now, let me just, this thing is behaving badly. All right. So for systems where the transfers function is not known, which is almost every system. Um, it would be a challenge to find some plant in the country where the transfer function is known. So how do you tune? What are the things that you look for? So when you don't know, you just know that you have the plant. First thing, you're going to have a set I and D in the controller to 0. So you're going to apply a step input or a unit response. Then, like I said, I'm summarizing. So you're going to turn up the gain until the all right. So you're going to turn up the gain until the so turn up the gain. The gain is the P, which is the K that we have up there. So you're going to turn up the gain until output is a pure sinusoidal wave. Now, in this wave, you are going to, so the system is oscillating. The book calls it P, so I'm going to call it P as well. So 4, measure the time period. Call it PCR, critical time period of the oscillation. 5, note the gain K on the controller. All right. So these are the steps that you would take if the transfer function of the system is not known. All right. So systems where the transfer function is not known, these are the steps that you would take. You take the system, apply again, turn up the gain until the thing start to oscillate, and then measure the time period of oscillation and measure it and write out the gain at which that oscillation occurred. All right. So if you note PCR and you know K, note K, then um, if I go back to the yeah, so we just summarize what is there. Same thing again. Your choice of controller depends on you. Um, so the value that you're going to get for TI, the value that you're going to get for KP, and the value that you're going to get for TD is going to be determined using this table. And I said that this table is empirically determined. So if you're just using a proportional controller, then you set the gain to be half of the gain that you got when you have your oscillations. And if you're setting for if you're setting for a PI controller, then it's 0.45 times KCR. Obviously, these numbers are not to be swatted. It's just a table that we would use. And TI, remember now, KP KI is equal to KP over TI. So we calculated TI with 1 over 1.2 of the frequency of oscillation. And if we were using a PID controller, then these are the values that you would use for PID controller. And remember that KD is equal to KP times TD. All right. So that is how you would do it for if experimentally, if you don't know the transfer function. But if you do know the transfer function, then you can analytically determine these things for yourself. So let me pick, well, let me not use the example that is here. So let me go back and use an example that I'm going to pull out of my head. Hopefully it works. All right, so we're going to do the same thing now. So for a known transfer function, so let's use an example. So this is the system, the transfer function. And the same things that we want to find now, but we want to work them out. We don't want to we want to work out what's the time constant for the system and what is the gain that will cause oscillation. So I'm going to just drop my system in my little box. So now, when I put the gain onto the system, what is the transfer function that I'm going to get? Well, cut a long story short, is going to be k over s cubed plus 4s squared plus 5s plus 3 plus k. And I multiply these two, k times this, and then 1 over 1 plus g. I'm going to end up with this. All right. Anybody remember how the road table go? Say yes.
Which table, sir?
Writing it down.
A long time that. No, sir, we don't remember that.
Mhm. Me remember it though. Yes, but you did do it last year.
Sir, is it the table to determine how many roots the equation has, how many stable roots?
If the thing is stable.
So remember, the women don't usually forget anything, you know.
Okay. Many years Zavina said nothing. Zavina, I remember not about road table. So your theory is false, sir.
No, Zavina is an exception to your rule, sir.
Okay.
The one exception.
The one exception. Okay. All right. So we're making up what road table is to determine if the system is stable. Well, we can use it because we want to determine what will make the system marginally stable. And marginally stable means that the system oscillates. Now remember we had said before that we wanted to find out the value of k that will make the system oscillate. So we want the value of k that will make the system marginally stable. So the question that we want to answer is what value of k makes the system marginally stable. So we can use the row table for that. Now, if you don't remember, they put in the s cube column, you write down the highest power that we have is s cube. So you have s cube, s squared, s to the 1, s to the 0. So in the s cube column, we put 1, the coefficient of s cube, which is 1, and the other coefficient going down as 5. And in the s squared column, we put 4, and the other one that is there, that is 3 plus k. So no matter what it is, we always write them, right? If whatever power we are in, we always write down every other term going down. Right? So in this case is 1 and 5 for s cubed, and for s squared is 4, and the next term, skipping over the next term, is 3 plus k. Now, how do we determine the value that goes into these points here? Well, same like you're finding matrices, but you have to start do it in the reverse order. So this 4 here, so consider this to be a matrix. We're going to do the, so we're going to do the determinant, but we're going to start with the subordinate diagonal first. So let me call this x. So x is going to be equal to 4 times 5 minus 1 times 3 plus k. And the difference is now we're going to have to divide by the pivot each time. So this is going to be
So instead of divide by what, sir?
the pivot. We start with the pivot
Okay.
and go across. And then when we finish, we have to divide by the people. So that's 20. I don't know if that is what your lecturer call it, but we can call it that.
Multiply by 1 over pivot.
All right, cool.
The control.
Same thing. So this one is 17 minus k over 4. Now there's nothing over here. So normally we would say there's this times, but then it's times 0. So this would be 0. Because there's the next column would be we are multiplying by the numbers that are in the one before. All right, so let me take a part of these markings here. All right, now we're going to do the same thing, and we're going to see, so we end up with a. All right, so now it's going to be this one equal plus is 17 minus k over 4 times 3 plus k minus 0, because 4 times 0 is 0, divided by 17 minus k over 4. And these two cancel. So we're going to end up with 3 plus k. And we always end up with that. Whatever is here, end up down here. So this is our route table.
I have a question. When I just started the table, you say 1 and 5 because they use the S3, S cube, then I skip 1, I end up with the 5. And the S squared now is 4, and then you skip the 5. So why when I reach S to the 1, write down the 5, and then skip 3 to the 3 plus k?
No, we write down until the first 2 rows is the written down rows.
Oh,
That is how it works.
okay.
Every other row after that is calculated.
Okay, all right.
No. No, the thing, row table tell you that if you want the thing to be stable, then all of these have to have the same sign. So all of these would have to be positive if the system is stable. If there's one negative in here, then it is unstable. So what it says, if our concern right now, if there is a 0 in the first column, system is marginally stable. If there's a 0 in the first column. So now, it's only, so either 11 minus k over 4 equals 0, which implies that k equal 11, which is the valid way to use. Or 3 plus k equals 0. So k equal -3, which is not the valid way to use. So we're going to use this value. You will see why.
I think part of the 17 rub off, so it look like 11 now.
Oh, lie. 17. I throw a 17. I'm gosh. I would have messed up the calculation badly. So this is the 17 is the value we're going to use. Because 17 minus 17 gives me 0. So k equals 17. You will see why is it that we don't use k equal 3? All right. So now, so we find that is what the book called PCR. So we're going to call it PCR. So we find PCR. So now the next problem is to find the frequency of oscillation. But again, from controls or from signals, that we know how to find frequency whenever we give a system. So the system characteristic equation. Write that down first, and then we discuss what we do. We had the system characteristic equation is S cubed plus 4 S squared plus 5S plus, now we're going to use this 17. 3 plus K, so that is 3 plus 17 equals 0. You see when we solve the problem, if we use K equal minus 3, it's going to be 3 minus 3, and it's going to, so this part of this is going to cancel, and that is going to lead us to a trivial solution. So we always use a number that, for K, that doesn't cause this value here, the constant term, to drop out. So the system characteristic equation is S cubed plus 4S squared plus 5S plus 20 equals 0. To find the frequency, what you are told is you must replace S by J omega. So we're going to have J omega cubed plus 4 times J omega squared plus 5 plus 5 times J omega plus 20 equals 0. Now, J times J times J, this is minus 1. So this is going to give me minus J omega cubed. And J times J is minus 1, so this is going to be minus 4 omega squared plus 5 J omega plus 20.
So J times J no plus 1.
Minus 1. I squared.
Wait. I no minus 1, sir.
No, I squared.
So minus 1 times minus 1.
All right. So we're going to put the real parts together and imaginary parts together. So this is going to give me 20 minus 4 omega squared plus J, take out the J, is 5 omega minus omega squared, or sorry, omega cubed equals 0. So for the system to be 0, then 20 minus 4 omega squared is equal to 0. Or 5 omega minus omega cubed equals 0. You can see if you do the maths right, then the two things will work out to the same thing. So we're factorize. So 5 into, 4 into 5 minus omega squared equals 0. And this is going to be omega into 5 minus omega squared equals 0. So 5 minus omega squared has to be equal to 0, or omega squared equal 5, which implies that omega is equal to the square root of 5. So that's the frequency of oscillation. Okay, we take it to where the textbook take it. Oh, remember, sir, record 2 pi f, which is 2 pi over t, is equal over t equal omega. So if I want t is equal to 2 pi over omega. So therefore, t, which we call in PCR, is equal to 2 pi over root 5. So we want a PID control. So I'm going to look up back these things here. Excuse me 1 second. I hear the police at my door.
You might not come back. People say police them do, I mean, he might not come back, you know, so.
Yes, sir.
So which was Saturday? School?
I think so.
Oh.
All right. So, yes, the police waiting at me outside. So, oh, you see on Route 5. But, all right. So, I was going to do the calculation, but the calculation is done here. Oops, sorry.
Plane just crashed with the coke.
No, they gone already. You know, crash. It land. Who tell you say it crash? All right. So why we keep on doing this? See, if I say the plane crash, I get confused.
Everything crash.
All right. So our KCR is equal to 17, and our PCR is equal to 2 pi over root 5. And we, like them, want a PID controller. So KP supposed to be equal to 0.6 times the 17. 76 is how much? 76 is 42.
Plus 42. 10 plus 4.2. 6 plus 4.
Well,
Two.
we can-
10.2.
So that's 10.2.
Is that? Come on, man.
GI is equal to 0.5
So we
times
can calculate.
2 pi
that?
over root 5, which is going to give me pi over root 5. That's an exact answer. So we're going to keep it there. Work it out to three decimal places for me. And
Three-
TD. Mhm.
2.8. 2.80.
You sure?
Sorry, 2.81.
Pi divided by root 5?
Oh, pi.
Sir, I got
1.404.
04.
Yeah, 405.
Yeah. 5. 405. Sorry about
405.
Yeah.
All right. And then divide that by 4.
Not a long
0.3512.
All right. So now we want K. We want Ki. So Ki, we said that was Kp divided by Ti. So Ki is equal to Kp divided by Ti, which is equal to 10.2 over 1.405. How much that equal to?
$7.26.
7.26. And this is Kp times Td, which is going to be 10.2 times 0.3512. What that equal to?
3.582. 3.582.
3.582. So Kp is 10.2. Ki is 7.26. And Kd is equal to 3.582. So those are the values that I'll put in the controller. It was a PID controller. All right. So what I'm going to ask you to do is look at this one, this example that is here. As you said, them do the same things. Should have filled in 0 and 0. It's the same things they use to determine KP, KI, and KD. All right. All right. So we're not catching enough COVID and things, so I suspect that the university is going to say that they're locking for the next. Well, they've said they're locking for the next couple of weeks. So we are going to be, after next week, we're going to be embarking on the project where we want what I want to write. So we're going to be looking for a theoretical project. Beginning of the term, we did things would have worked out different, so we would have something more practical for you to do with all of these. So next week I'll give you the theoretical project for it that you must do. I'm going to want you to do. And that is going to be your last grade.
So when them supposed to disembark?
All right. Question is asked when the term finish.
When they're supposed to disembark? You say them are going back, so I wonder when them are supposed to disembark.
Somebody here talking pure foolishness. All right. So we're going to stop there for today. Next week, we're going to talk about where it is chapter 13.
Okay, so.
Sir, excuse me. How much people are allowed?
Okay, I hear you. Talk again.
How much people are allowed to be in group for the project?
How much?
Okay, no.
To be in group for the project.
Groups.
Yeah.
Oh, you hear me say the word group?
Oh, individual. All right, no problem.
What is it now?
Or the government say you can't be in a group, you know.
All right.
Gotcha.
So we have to abide by what the government say. How would you see? How would you see that song?
Sir, group of 5, Andrew said last night, you know.
Eh?
Andrew said group of 5 last night.
A 5 or 6 himself?
Even better.
No, lie, 10.
10. Yes, sir. 10.
But England said the 6.
Group size.
England say you can't be in more groups of 6. So somebody was asked why everything has 6 in England. You can't be more than 6 feet apart. You have to be in a group of 6. You can't have everything has 6. So what's with the 6 then?
Oh.
But
6 is real, you know, sir.
6 is real.